This is 7.2, sampling distribution of p hat. If you choose an SRS of size n from a population size capital N with the proportion p of success, where p hat is the sample proportion of success. The mean of the sampling distribution of p hat is mu of p hat equals p. Remember, p again is a population proportion. Now, to help us out, we have conditions. The standard deviation of the sampling distribution of p hat is equal to p times 1 minus p divided by n, as long as your sample size is less than 10 times the population size. As n increases, the second condition, as n increases in the sampling distribution of p hat becomes approximately normal. And this condition is we can use a normal approximation as long as n times p, your sample size times the proportion, is greater than or equal to 10, and your sample size times 1 minus your proportion is greater than or equal to 10. Here's an example of a distribution of a bunch of p hats. That's a sampling distribution. The sampling distribution of a statistic is the distribution of values taken by the statistic in all possible samples of the same size from the same population. In other words, it's a distribution of sample. Now, what's a statistic? Well, the statistics we're going to focus on sample means and sample proportions. Now, how do we describe a sampling distribution? Well, go back to chapter 1, Cuss and BS. Here's a couple examples of some sample distributions. This is a sampling distribution of sample mean. In other words, it's a bunch of X bars put together. Now, I made it look normal because that's what we want it to look like, and we'll figure out ways how to make it look normal later. And here's a sampling distribution of a bunch of p hats. In other words, a sampling distribution of sample proportions. Once again, I made it look normal because that's what we want to do. And remember the rules for that. N times p is greater than 10, and n times 1 minus p is greater than 10, and then we can make that normal as well. Notice the mean of this sampling distribution is mu, and the mean of this sampling distribution is p. Alright, let's put this into work. Let's do a real problem. Let's say that the proportion of white gumballs is 15% in a gumball machine. Would you be surprised to get a sample proportion of p hat of 10% in a random sample of 100 gumballs? Alright, here it is, your dream gumball machine. If you're a gumball addict, there you go. I think we can see that's pretty big. I think this must be Rohan last year as a freshman. You see that the mean of p hat is equal to p, which is 15%. Now here's our first condition. Because there are more than 100 times 10, which is 1,000 gumballs, I think there's 14,000 in there, we can use the formula p times 1 minus p over n for our standard deviation. So 15% times 85%, ignore the parentheses I forgot to close, over 100 equals 0.0357. That's our standard deviation. It's 3.6%. Because n times p, which is 100 times 0.15, is 15, which is greater than 10, and n times 1 minus p, 100 times 0.85, is 85, is also greater than 10, we can use a normal curve. Remember, a normal curve is standardized. Z equals x minus mu over the standard deviation. So, the probability that z is less than 0.1 minus 0.15 over 0.0357, which is your standard deviation, is equal to the probability that z is less than negative 1.4, which is 0.0807, which is 8%. Don't forget your graph. There's an 8% chance of getting a sample proportion p hat at or below 10% if the true proportion is 15%. So while you may be a little surprised, it's not too uncommon. 8% is not too small.